Thank you, guys. So, yeah, well, my name is Josep P. Rodriguez. I'm a senior security consultant in IOActive. And today we are going to see how I broke this WingOS device, the operating system. So this is a really technical talk. So we will see a lot of assembly instructions, IDA Pro screenshots, stuff like that, memory corruption vulnerabilities. So I really hope you will enjoy. So the topics that we will cover today, first I will give a small introduction to this WingOS. Then we will describe some scenarios and attack surface that we have. Then with full technical details, I will describe some vulnerabilities. Then one exploitation of one of those vulnerabilities with a short demo, and then some conclusions. So first of all, what the hell is this WingOS? So basically, it's an embedded Linux operating system with its proprietary stuff in the user space and kernel as well. It was created by Motorola, but nowadays it's property of Extreme Networks. We will discuss about this in a minute. And the architecture is MIPS N32. Mainly it's used in wireless access points and controllers. And as far as I know, there's no public information about vulnerabilities and its internals and stuff like that. From their website, from Extreme Networks website, we can get more or less a high-level details of what is this WingOS, where they say like it's the next generation in the evolution of the WLAN architectures. It's a pretty cool operating system, blah blah. But we don't have like very useful information about its internals. Basically, we have a typical web interface where we can set a lot of stuff. I mean, the web interface is pretty huge, but this research is not focused in the web interface. I wanted to focus in something else, where we also have the typical command line interface, similar to a Cisco router, for instance, where we can connect through SSH and execute a lot of different commands. And this command line interface is restricted, meaning that from here you can't access to the embedded Linux system that is running in the background. Then devices that are using this embedded operating system, well, from the Extreme Networks website, we can see like a list of devices that we have, more or less. But these are not the only devices using this OS, because as I said, Motorola created this operating system. So we have Motorola devices as well using this operating system. But then Zebra bought this part of the business from Motorola, so we also have Zebra devices. And then in the end, Extreme Networks bought this part of the business from Zebra. That's why we have like a lot of different devices from Motorola, Zebra, and Extreme Networks using this embedded operating system. But also we have the Contron device. The thing is, this research started mainly because of this, because Contron is a multinational. They make a lot of embedded devices for different industries, especially for the aircraft industry. I saw this device, which is the Cap and Connect, which is an access point that provides Wi-Fi access to the passengers of the aircraft. But then I realized that right inside this box, we have a Motorola AP7131 access point running the WingOS operating system. So where we can find these devices? Well, first, as I said, we can find in aircrafts. It's widely used by many airlines around the world. We can see from some pictures on the internet, like sometimes they have even the Motorola access point over there on the ceiling of the aircraft. Some other pictures where we can see the Contron device, the Cap and Connect box, as well on the ceiling of the aircraft. But besides the aircraft, these devices are used in a lot of different places, like smart buildings and the healthcare, government, universities, I don't know, a lot of different places. And we can check this information from public information on the internet, from, for instance, case studies from Motorola, where we can see that these access points are used in the New York City subway, for instance, in container ports, global electronics manufacturers, universities, even in mines, In cities as well, for instance, in the Saigon city in Vietnam, they have more than 1,500 access points out there to provide Wi-Fi to the citizens, hotels, casinos, more universities, even providing the guest network for military bases. So yeah, it's like in a lot of different places. So for the attack surface and scenarios, I divided in two, the aircraft scenario and the rest, mainly because the aircraft scenario is, it has its particularities, but all of this is focused in the remote pre-auth vulnerabilities that I found and the ones that we will describe in a while. So in the case of the aircraft, if the attacker has physical access to the device, then if the attacker connects a cable to the device, he can exploit all the issues that we will describe. But of course, in the case of the aircraft, as we saw, normally the device is on the ceiling of the aircraft, so it's less likely, right? But also, it's possible to exploit these issues through the Wi-Fi connection. But also, another attack surface would be pivoting from the satellite modem to the access point from the ground. Let me explain this a little bit more. So I don't know if you guys were aware about this research, but my coworker, Ruben Santamarta, presented this research where he was able to, from the ground, with a regular internet connection, he was able to hack airplanes that were flying on the air, okay? Basically because the satellite modems of these aircrafts were exposed to the internet, so he reverse engineered the firmware of the satellite modem and he found a backdoor. So he exploited that backdoor and he was able to get remote code execution in the firmware of the satellite modem. And then once you have remote code execution in the satellite modem, you can pivot to other devices that are in the aircraft. For instance, my access point. So with this attack, you could also exploit the vulnerabilities in the access point that is in the aircraft from the satellite modem, using a regular internet connection from the ground. And this is the architecture where we can see where indeed the satellite modem has connectivity to the access point that has the WingOS vulnerabilities as well. The rest of the scenarios basically outdoors and indoors access points. So again, if the attacker has physical access to the device, which is more likely in outdoors access points, then connect the Ethernet cable and exploit the issues, but also through the Wi-Fi as well, and through the internal network. Let's say the attacker is inside the internal network somehow, and he has connectivity to these devices, then he can exploit through the network those vulnerabilities. So let's start with the vulnerabilities. The first one is a hidden root shell kind of backdoor. So which allows us to, from the restricted command line interface that we saw before, to get access to the embedded Linux that is running in the background. So from the attacker's perspective, if the attacker compromised somehow the command line interface, like compromising the credentials, for instance, it's okay. You can do a lot of stuff. But having root shell, we can say that the device is completely compromised, right? But of course, this one is not a really critical issue, but it's very important for the research process, because when you are working in a vulnerability research with an embedded device, having, in the case that it's running embedded Linux, if you have a root cell, it helps a lot the research process because you can do a lot of stuff in a dynamic way. So looking something on the internet, I saw in some forums that some guys were asking questions about this service star shell command, where some guy was saying that gets you into the native operating system, but Motorola may not disclose the required password to customers. That's more or less all the information that you can see about that command. Even if you read the official manuals for these devices and the operating system, you can see that indeed there's a star shell command which provides shell access, but that's all the information that you get. And when you execute the command, you can see that, yeah, you got the last password used, and you got this password lowercase letters with this MAC address, and then the password prompt asking for the password. That's all you got. So one might be thinking here right now, like, okay, so it's already telling me which one is the password. It's password in lowercase letters. But no, that's not gonna work, and we'll see why. So what we just need to do is to identify the binary that executes this code, and then reverse engineer all this stuff. So here we have where this particular binary is asking for the password for that service start cell command. And we can see here that it's going to execute this validate map password function. And depending on the return value of this function, it's going to hit this basic block where we can see that the root cell is going to be executed. So inside that function, we can see that it's going to call another function called get last map password, where it's going to access to this file, the etc2 IMIS password, which the content of that file is always the default value in every WingOS device, which is this particular string here. So with the content of that file, what it's going to do is execute all these instructions in this loop. Okay? So to play around with Unicorn, what I did was emulate these instructions, feeding it with the content of the file, providing the content of the file. For those who doesn't know what's Unicorn, it's an awesome framework which is running QEMU in the background, and it allows you to emulate several different architectures. It's pretty cool and pretty useful sometimes for some particular stuff. So yeah, with in this case with the Python API, you can like provide instructions that you want to emulate, and also provide the input, which is in this case the content of the file. And then after the emulation, we can see the result, which is these hex bytes. So if we look carefully about this result, we can see that in the end, this was the content of the file, and this is the result. So basically, it's meaning that the content of this file are hex bytes, but in ASCII. Okay, so this is the result, as you can see here, which is basically the same, A2061, A2061, blah, blah. Okay, so after that, the code flow, what it's going to do is to decrypt that result with using an RC4 algorithm, using as a key this hard-coded key. Hi, Sabina, how are you doing? Bye. Then the result of this decryption is going to be the string password in lowercase letters, which makes sense because if you guys remember, we were in the function get last password, and that's why it's getting password, and we were having this prompt like saying last password use password in lowercase letters. Okay, then after that, the code what it's going to do is get the MAC address of the device, and then do in this loop these operations where basically it's adding 1 to the second byte of the MAC address, 2 to the third byte of the MAC address, and so on. And then using that MAC address with those operations as a key, it's going to call another RC4 decryption routine, but in this case, it's going to decrypt the string password. And finally, with that result, it's going to execute these instructions where it's basically making sure that the string, the resulted string, it's lowercase letters. So, for instance, for my device, for my particular MAC address, this is the valid password, as you can see here in lowercase letters. And then you can access to the Linux root cell through the command line interface. But when the password is granted, the code flow, we can see that it opens again that IMIS password file, and then it's going to encrypt again with RC4 with the same hard-coded key. Hi, Sabina, how are you doing? The password that the user typed, meaning that the next time you're going to execute the command, the password is going to be different. So that's why I call this like a kind of a dynamic password, because every time you execute the command and you provide the correct password, it's going to change. And you will have to do all these operations in order to calculate the valid password. So this describes more or less in a high level the overall process, because it's a little bit weird. But yeah, so to make it persistent, in the code we can see that if you create, since we have now access to the Linux root cell, we can create this allow root file in the directory etc. And then we can see in the code that it's not going to ask for the password anymore. So we can make it persistent very easily, creating this file. And we can see now, executing from the command interface, the service start set command. It's not asking for the password, and we can have access to the root cell. Okay, so now we have access to that root cell. So we can start to analyze more stuff in a dynamic way. We can debug processes. We can see which services are running by default. So we can see, for instance, that the UDP port 3799 is listening in all the interfaces by default, which is the radio interface module process in this case. So I just started to reverse engineer where this binary was reading from the socket, from the regv from API. So yeah, I'm following the code. We can see that there is a particular memcpy where the source and the size are user controlled, and the destination buffer, it's a stack buffer, so it's a pretty straightforward stack buffer flow pre-authentication. I mean, there is no need, the attacker doesn't need any kind of authentication to exploit this issue. So basically, the typical reverse engineering stuff, like here's when the binary is reading from the socket here in this red block, and here's where we have the particular memcpy where you can trigger the stack overflow. So you just need to analyze all this data and provide the right bytes in your Python client, for instance, to reach that stack overflow. So in this case, this is the Python client that triggers that stack overflow. But this particular stack overflow only affects old versions of the firmware. But I reported this because this was affecting to the control devices, the ones are used in aircraft. That's why basically I reported. But also there is an interesting thing about this issue, because in newest versions of the firmware, we can see that they tried to fix the issue, but they committed another mistake, where basically we can see that they are checking here the size of the memcpy, which is user control, and if it's bigger than F36, then instead of calling or reaching the memcpy, it's going to call this assertprint function. But this function, what it's going to do is, in the end, killing the process. So now, okay, we can trigger the stack overflow, but we can kill the process. Not a big deal, right? Because if we kill the process is going to restart it immediately. But the problem here is that there is a watchdog system in this OS which checks if the RIM process, this process, is alive, because it's a critical process for the OS. So if we execute this Python script like 2 or 3 times in a row, then the watchdog will check that the process is not alive, and it will reboot the whole operating system. So we can reboot the whole operating system all the time. That's why I call this like a kind of global denial of service. Okay, so now the Mint vulnerabilities. When I was reverse engineering several binaries of this operating system, I just saw that some of them they were listening and reading from sockets, but tracing those sockets, I realized that they were using non-standard values for domains, for instance, and I saw also some references such as local Mint address. So I didn't know what the hell was this Mint thing, and I wanted to know. So about Mint, there is no much information on the internet. I mean, there's some high-level stuff, but nothing very technical or about its internals. But in the end, it's a layer 2, layer 3 proprietary protocol created by Motorola as well. And we have 2 different levels, level 1 for VLAN and level 2 for IP. But Mint basically is for communications between devices. Like, as we can see here in this image, they use level 1 Mint to communicate between access points, or level 2 Mint between controllers, between them, or to communicate controllers with access points. So, as I said, it's a layer 2, layer 3 proprietary protocol. They created their own socket address family, which is, in this case, the AF Mint. So it's implemented in their kernel. And it's a datagram socket. So we have the port as well, but the address in this case is the last 4 bytes of the MAC address. So the idea here is we want to create a client, and we want to be able to use this Mint protocol to communicate with other access points, for instance, through Mint, and exploit potential issues that we would find in the future. So we have several options here. First, we could just reverse engineer the kernel and try to build your own client, which is possible. Then try to emulate the whole operating system and kernel and use it in your Mac or your Linux box or whatever, which is also possible, but it might take some time. And another option could be to find a way to build a client using the OS kernel, like using an actual device, which is the option I took because it's the quickest. I'm very lazy. So yeah, in my case, I'm going to use my own device to attack other devices. But as I said, this is not mandatory. You can build your own client in your Linux box, for instance, if you want. So the attack scenarios using Mint, basically, in my case, since I am using my own device, let's say I connect my device through the Ethernet network or through the wireless to other network where I have other access points or controllers. Then, with that, then I can establish the Mint link and exploit potential Mint vulnerabilities. But other option could be, let's say the attacker remotely compromises one WingOS device, like an access point or controller, and from there he can pivot and exploit Mint issues in other devices. One particular thing about controllers, they are very interesting targets because if we compromise one controller, then we can compromise all of the access points that are connected to them, which could be dozens or hundreds of access points. And the controllers have the same vulnerabilities that we were talking about and the vulnerabilities that we will discuss in a minute. Okay, so to create that Mint client, remember I'm using my own WingOS device to communicate with Mint to other devices. Luckily, we have a native library which allows us to import the socket through Python and communicate with AF Mint sockets. So with this Python script, for instance, we can, as we can see here, providing the Mint address in decimal, which is remember the last 4 bytes of the MAC address, the port, and then we can import the socket, and we can, with this, communicate through Mint with our device to other devices. One particular thing is that we expect to have Mint enabled in scenarios where we have several access points and controllers. But I wanted to check also if a standalone access points might be using Mint as well. And yes, indeed, it's still technically possible to have standalone access points using Mint or with Mint enabled. So to establish the Mint link, we just need to know the IP address of the target. From the command line interface, as we can see here, in the attacker's device, executing these instructions, controller host and the IP address of the target, then the Mint link is already established, and we can see that the victim and the attacker, they see each other through Mint, and that's all you need to establish the Mint link. But this is not the only way, because based on the documentation, also this Mint link can be established in an automatic way, meaning like if the other devices see a new device connected into the network, they will establish the Mint link in an automatic way. Okay, so now we are able to communicate through Mint with my device to other devices. So let's see if we can find more vulnerabilities in these services. So we just need to, again, reverse engineer those binaries that are listening through Mint services. For instance, here we have one function of one particular process, the HSD process, which is pretty big, as you guys can see here. And we have the typical switch case statement for the protocol, this typical pattern. Okay, so after some time of reverse engineering, several memory corruptions, pre-auth heap overflow in this case, where again, another MCPY where the source and the size are user controlled. And in this case, as you can see here, the destination buffer is a heap buffer. So it's a pretty straightforward heap overflow. But The problem that we have is that in order to reach that particular MCPY, the code flow is gonna, we have to hit this case in the switch case statement where this get session by MAC function is gonna be executed. And the problem is that this function checks if the MAC address that you have to provide in your payload is in a list of MAC addresses authenticated. If it's not there, then you won't reach that MCPY. So that's a problem because the MAC address that we provide in our payload is not in that list. So we have to find a way to add that MAC address in that particular list. Luckily, there is another function in the switch case statement which we can reach without any kind of authentication, which is called this function session alloc, where we can add our MAC address to that list. So with this Python script, for instance, as you can see here, this is the fake MAC address that I'm adding to that list, which is AAAA 414141. And with this, we can add that MAC address to the authenticated list of MAC addresses. And now we can reach the MCPY with the heap overflow vulnerability. As you can see here, guys, the MAC address is provided as well in the payload. And now we will trigger the heap overflow. And here we have the crash of this particular heap overflow. More issues, well, there are more memory corruptions, more heap overflows, like this another one, in another different min port. And here we have the crash, so pretty much the same, all of them without any kind of authentication. Now, this is the vulnerability that we will exploit in a couple of minutes. Basically, it's a Stack Overflow, where we can see, again, another memcpy where the size and the source are user control, and the destination buffer is a stack buffer in this case. But in this case, the source comes from the heap, and the problem is that in order to overflow the return address in the stack, we have to overflow as well the heap buffer with that memcpy that we were discussing before with the heap overflow vulnerability. So here it explains better the overall theme. So this is a memcpy where the destination buffer is a stack buffer, as I said. So if we want to reach and overwrite the return address in the stack, since our source comes from the heap, it has to be big enough. And then we will overwrite the next chunk's metadata and the next chunk. So this might be cause a problem because if the libc sanity checks are in place, then it could crash and ruin our exploit. But in this case, it's not going to be a problem because if we execute the exploit, the chain of the exploit more or less quickly, the libc sanity checks won't be triggered and it won't ruin our exploit. So for the exploitation, this embedded OS, like many other embedded operating systems, it has no exploit mitigations such as ASLR, NX, stack canaries, and stuff like that. So we could think, okay, we just need to jump to our shellcode and that's it. But no, because in this case we are dealing with MIPS exploitation, and there's one well-known problem in MIPS exploitation, which is the cache incoherence problem. So in MIPS processors, we have two different caches, the instruction cache and the data cache. And normally our payload, our shellcode in this case, is going to be stored in the data cache. So the problem is that basically that if our shellcode or part of our shellcode is in the data cache, it won't be in memory. So when we try to jump to our shellcode, we will execute other instructions, but not our shellcode, and then the exploit won't work. That's why we need to flash the data cache where our shellcode is going to be, and make sure that our shellcode will be in the memory. There are several techniques to do this. We can fill the data cache to flash it. We can call a blocking function such as sleep using ROP. ROP, why? Because basically the same. I mean, we might have the same problem. If we don't use ROP, if we write a small shellcode to call sleep, then that small mini shellcode could be in the data cache. So that would be the same problem. That's why using ROP, we won't have that problem to call this sleep syscall to flash the cache. And then after calling sleep, the data cache will be flashed, and then the shellcode will be in memory. So for the ROP, in IDA Pro, we can see that in the function where we have the Stack Overflow, we can see easily which registers we have control with, which is pretty useful for the ROP exploitation. I'm using gadgets, ROP gadgets from libc in this case, because the libc is loaded by the binary, of course. So basically, the libc gadgets, what are doing is calling the sleep function that we were discussing to flush the data cache. And then after calling the sleep and flushing the data cache, it's going to jump to our shellcode, which finally will be in memory. For the shellcode, I'm using a regular shellcode reverse shell, which will connect back to our listener. But the problem with the shellcode is that all the shellcodes that we have out there for MIPS and Linux won't work, mainly because we are dealing here with the MIPS N32 ABI. So with this ABI, we have some particularities. For instance, it uses 64-bit registers, but it uses 32-bit memory addresses. But also, it uses different syscall codes. That's why the shellcodes that are normally out there, like in Metasploit or ExploitDB or whatever, they are using different syscall codes, and that's why your shellcode won't work. But well, we can solve this issue very easily in different ways. For instance, we open the libc in IDA, we can see the syscall codes for the syscalls that your shellcode is going to be using. And then you modify that in the shellcode, and then your shellcode is finally working in this particular MIPS N32 architecture. OK, so for the exploit, remember, I'm going to use my own device, but this is not mandatory. You can use your own laptop if you want, if you build your own client, a Mint client in this case. And so let's say I'm connected through the Ethernet or through the wireless to some network where I have other access points or controllers. I'm going to exploit a Mint Stack Overflow vulnerability without any kind of credentials. So this is more or less the overall process, where we have the target, which is providing a Wi-Fi network. So the attacker's laptop, for instance, my Mac, is connected to that Wi-Fi. Then the attacker's device, my WingOS device, is connected to my Mac through Ethernet cable using the MacOS sharing feature. So the attacker's device can reach the target through the Wi-Fi that the attacker's laptop is connected to. Then 3 basic steps. We run the netcat listener in the attacker's laptop, where the reverse shell is connected back. Then we run the Mint exploit in the attacker's device. Remember, we are using our Python client in the WingOS device. So we are able to communicate through Mint. And then the exploit is going to exploit over the air the Stack Overflow in the target. And then the reverse shell will connect back to our listener. So let's see a quick demo. So basically, you guys can see here that I'm connected to this Wi-Fi, the multi-test Wi-Fi, which is the Wi-Fi that the access point target is providing. OK, so in the Mac, we can see the configuration where basically I have the network 0.175 for the Wi-Fi, and the bridge 100 interface that the MacOS sharing feature enables, where we have the 0.2.1 network. So the attacker's device, this is my device. From the command line interface, we are going to execute some commands, like, for instance, to show the IP address that the device has, which is the 0.2.24, because it's connected to the bridge interface of the MacOS sharing. So we're going to see that the Mint link is already established. So basically, the attacker's device can reach through Mint the target, which is this one, the 0.1.139. And we can even execute the Mint ping command from the command line interface to see that indeed we have Mint connectivity. Then the netcat listener in my Mac, which is listening the 8080 port. Now I'm going to access to the root cell with the service start shell command, as you can see here, because I'm going to run the Python clients and the exploits from the Linux root cell that the device has. Now, the exploit basically it sends 3 different Python scripts. If you remember, first, since we have to overflow first the heap, we're gonna execute one Python script which adds our fake MAC address to that particular list that we were discussing before, so we can reach the memcpy for the heap overflow. Then we will trigger the heap overflow. We will overflow the heap with the rob gadgets and the cell code and stuff. And then finally, we will trigger the stack overflow, which that particular memcpy will get from the heap buffer, the shell code, and the rob gadgets, and then it will exploit the stack overflow. And here we can see the second Python, where we can see that indeed we have our shell code and our rob gadgets which will be in the heap buffer and then used for the stack overflow. Then if we execute the 3 different Python scripts, then we can see that in our netcat listener, we have indeed the reverse shell as root, of course. So the exploitation worked out. So yeah, that's one particular Mint vulnerability exploited over the air without any kind of authentication. All right, so yeah, this is what we're discussing. So as a conclusion, Extreme Networks, which is the current maintainer of this operating system and devices, they provided several patches. In this link, you can see more information about them. At first, they had some mistakes. They didn't believe that these issues were it was possible to exploit over the air, but in the end, they realized that it was possible, and they changed all this information. But yeah, basically, most of the critical issues are fixed. But again, still there is a lot of room of improvement in this embedded operating system, because besides all the vulnerabilities that we saw here today, there are more critical issues. But yeah, I don't know, hopefully with these lessons learned, most of these issues will be fixed in a proactive way, and we will have more WingOS devices, more secure WingOS devices out there. So that's it. Thank you very much.